G'day and welcome back. Today, we were going to talk about mass, but there's been a change of plans. When putting together this second episode, I realised that the next 3 episodes require the understanding of 2 fundamental principles, inertia and momentum. So let's firstly work through that. Inertia is how much effort it takes to move an object, and in the context of a racket, we think about how hard it is to lift, manoeuvre, and swing. The premise is that the heavier something is, the harder it is to move. Momentum is the amount of energy that an object has when moving, and this depends on the object's mass and the speed that it is travelling. In this case, we apply this to a swinging tennis racket and a flying tennis ball. Let's imagine a simple system. A ball is travelling towards a stationary tennis racket, so it's like hitting a very lazy volley. To simplify this further, we make the system linear by removing the handle so that the centre of mass is in the middle of the string bed, and make the object smooth and solid to remove friction and deformation. In physics, we describe this as an elastic collision. In an ideal elastic collision, the total momentum is conserved. So now let's combine our principles together into a single scenario. We have the racket representing team inertia, and the moving ball representing team momentum. When these objects collide, no matter what the mass of the racket, it is deflecting backward to the left, but how fast depends on its inertia. But where the ball goes will depend on the relative amount of momentum to the inertia of the racket. More inertia, and the ball is bouncing back to where it came from, and the racket is rebounding less. Less inertia, and the racket is rebounding faster, and the ball is continuing on its merry way. Unlike this scenario, in real life, rackets don't just hover in the air. They are held and supported by a hand holding a grip, which will transfer the momentum to the inertia of the body, which will then transfer some of that momentum to the friction of the feet to the ground, and so on. So let's add a supporting hand behind the racket. When the ball collides, some of the momentum is taken up by inertia. The rest is transferred to the hand to prevent the racket from moving. What we can see here is that the heavier the racket is, the less momentum is transferred to the hand. Here we have a demonstration of how mass increases stability. Let's now transition to both objects moving towards each other, creating opposing momentum between the racket and ball. Let's use the hand to propel the racket. It takes more effort to push a heavier racket because of inertia. The increase in effort required is a demonstration of mass decreasing manoeuvrability. So say we want to hit the ball harder, then we have to increase racket momentum. But how do we do that? Momentum is proportional between mass and velocity, so we can either increase mass or increase velocity. We've also established that heavier mass is harder to accelerate, while lighter mass is easier. So let's look at the 2 extremities of how we could achieve momentum. We can either push less mass at a higher speed, leaning towards a more manoeuvrable racket, or push more mass at a lower speed, meaning the racket is more stable. Let's apply opposing momentum to our collision. If the momentum is relatively low, the racket is still going to deflect backwards, although compared to the stationary racket, the deflection will be less and the ball will rebound faster. But once the momentum reaches a certain point, instead of a backwards deflection, we can see that the racket can overcome the ball and has enough residual momentum to continue moving in the same direction. This is an example of plow-through, where the racket has enough momentum to naturally continue in the same direction through the ball. Finally, we can visualize inertia versus velocity on a graph, where we can see that for a given strength of person, there is a maximum speed that they can swing, and that is sustainable up to a certain weight. Beyond this, the speed will fall away as the inertia is unable to be overcome by the person's strength. Since we have mass and velocity, we are able to calculate momentum, which we plot on the graph. We can see that momentum increases up to peak velocity, and that there's a weight range where the reduced velocity is offset by the increased mass, meaning that momentum still stays quite constant. Within this band is a space where you can add stability through mass, although you sacrifice speed and manoeuvrability, while maintaining the same momentum. A few things to consider. Your physical conditioning. How much weight you can handle will depend on your base strength and fitness. How much swing speed does your technique require? Longer strokes will require faster swing speeds. Flatter, more compact hitters don't need the extra speed. How much manoeuvrability does your game require? you're playing doubles, like to rush the net or take the ball early, then you can't afford to be slow. And a final consideration, when you're on the stretch, or you're blocking a huge serve and don't have time to prepare, more mass can help increase momentum and stability at those slower swing speeds. Let's summarise what we've learnt here. We're learning that mass in general has an effect on how much effort it takes to manoeuvre an object, as well as having an effect on how much momentum a moving object has. We have also learnt that there is not a fixed optimal balance of manoeuvrability and momentum, and that it will depend on your technique and playing style. The next layer on this onion is applying this to stroke mechanics, covering linear forces, weight distribution, and rotation and torque. Next episode, we focus on static weight, or the straight line representation of inertia and momentum. Hit like, share, subscribe. We're just getting started. I'll see you next time on It's Not Racket Science.